Okay, today's class is going to be about mainly about the transient and the transient model of the diode. So we're going to cover things like what is the capacitance of the diode, how does the diode behave in the transient behavior. We've looked at equilibrium so far, and then we looked at steady state. So in today's class, we're going to be going over the transient behavior. That's going to be the first part of the class. Then the second part of the class, we will start talking about metal-semiconductor junctions, which have diode-like properties sometimes and resistor-like properties in other times. All right, let's just end up like last time in class, we ended up talking about forward bias diodes. Then we talked about reverse bias diodes. And then we talked about two different types of breakdown mechanisms in reverse bias, a Zener breakdown and avalanche breakdown. So at this point, we have covered some of the major properties of the diode, performance parameters of the diode. Okay, and each of those performance parameters depends on design parameters. You know, if you want your bridge to be strong, you have to design it with certain types of materials, right? If you want, the diode has certain performance properties, performance parameters, and those performance parameters depend on how you design the diode, the design parameters. So the performance parameters are here on this left side here. You can see, can everyone see my mouse? Okay, yeah. These are the performance parameters on the left, and these are the design parameters at the top. Okay, now we're not going to go over this in class because I think that this is the thing to do. Well, I'm happy to go over it with everyone once everyone has had a chance to do it. So we can go over this as part of our review, you know, towards the end of the semester. But I want everyone to do this as an exercise at home. Okay, and then we can go over it. We can go over it later. The reason why I want you to do this is because this is the best way for you to understand diodes. From an engineer standpoint, okay? These are the things that the engineer has over his control. Okay, the doping level, okay, the NA and ND, the doping level on the P and the N sides. Then you can also control the area of the diode. How big is the diode, right? And then you can also control the material, or the material of the diode determines the band gap of the diode. Right? So the choice of these three things is going to determine all the performance parameters like the built-in potential, the depletion width, the saturation current, and so forth. So just to show you what I'm looking for here, this is the kind of thing I want you to do. So for example, we have the ability to control the doping of the diode. How does the doping change the built-in potential? If we were to increase the doping, what would happen to the built-in potential? That's right. Thank you, Lama. I see a lot of puzzled looks out there. So there's several ways you can go about this. You have to think about the design equations. All right. So I'm just going to put V0 is equal to KT over Q ln of NA ND over NI squared. Right? So that's how we calculate the built-in potential. So you can see here that it's a logarithm of NA times ND. Right? So what I would put here is I'd put an up arrow here. Up arrow means that as the doping increases, the built-in potential also increases. So you can think about this in terms of equations. You can also think about it in terms of physics. For example, look at the next one, for example. How does doping affect the depletion width? Does anyone recall?
Higher concentration, smaller depletion width.
Right. Higher doping leads to lower depletion width because you have a higher concentration of charges. And when you have a higher concentration of charges, the depletion width doesn't have to be as long to create a total charge, a total amount of charge. You were going to say the same thing? Yeah. So these are the types of questions I would probably ask you on an exam. So there's two ways you can explain it. If you're more the mathematical person and show me an equation saying like that this is, this equation shows that depletion width will decrease with doping, fine. If you're more the conceptual person, you think you can explain it by, just talking about the physics of the diode, that's also fine. If you know both, even better. All right, so, but like doping, if you increase the doping, the depletion width goes down. So this is the kind of thing I want you to think about. All right, so we'll come back to that, as we get closer to the final exam. Okay, so today we're going to talk about, as I mentioned, the transient behavior of the diode. Before we get into that, we'll talk about some of the circuit models of the diode. All right, as you know, in electrical engineering, you've seen these basic symbols: the resistor, the capacitor, and the inductor. They all represent a certain type of behavior in terms of like the relationship between voltage and current and so forth. So we have these symbols. So some of these elements have a linear characteristic, and some of them can have nonlinear characteristics. So a diode, the diode essentially has a nonlinear characteristic. We showed in last class that there's an exponential relationship between voltage and current. So engineers often prefer not to deal with nonlinear elements. When they have a nonlinear element like a diode, sometimes engineers will model that diode as a combination with an equivalent circuit model of linear components. Okay, and these are some examples of how that can be done. So this is the actual diode characteristic here on the right. All right, we know that you have the saturation current on the left, a small negative current, and then when you apply a positive voltage, you get an exponential increase in the diode. So this is an exponential function. It's nonlinear. As I mentioned, engineers often like to approximate nonlinear functions with piecewise linear functions. Does anyone know why we do that?
Easier to deal with?
It's easier to deal with, but like why? Think about your circuits. If you've taken a class like circuits 1, circuits 2.
You can increase or decrease the value to get like a specific results.
You're getting close. Yeah. You're saying increase and decrease of value to get a specific result. Yeah. You're getting close. You're getting towards the right concept. Do you all remember learning about the principle of superposition in circuits? Okay, I'll just say two things very briefly. The principle of superposition allows you to analyze a circuit. If the circuit contains all linear elements, the principle of superposition will allow you to look at the effect of multiple voltage sources, multiple current sources, and you can look at each one of them independently. It also allows you to simplify the circuits in ways that you can't do if you have nonlinear circuit elements. That's the first thing. Now, from the second thing is that this is, I would say, not just electrical engineers, but a lot of engineers and scientists prefer to work with linear functions because you can apply linear algebra and matrix theory to those types of things. And this allows you to combine and solve very complex problems by using a system of matrices. Okay, so those are some of the reasons why engineers like to deal with linear systems. So how do we represent this diode, which has a nonlinear IV characteristic, as as a piecewise linear function? So this is the actual equation that we're going for, the actual IV characteristic. One way, a very simple way you could approximate this curve, which is not ideal, well, pardon the pun, it says this is the ideal diode equation, but you could approximate this curve as just a flat line here and then a vertical line here. And that's what's being shown here. So the current is 0, when your voltage is negative, and then the current goes to infinity when the voltage is positive. So this is the representation of the ideal diode. The ideal diode is a circuit element. When we draw an ideal diode like this in a circuit, what that means is that the diode only conducts current in one direction. It's a perfect conductor in one direction, and it doesn't conduct current at all in the opposite direction. So when the voltage is negative, something that doesn't conduct current at all, the current's obviously going to be zero. A perfect conductor has infinite current at any non-zero voltage and any positive voltage, because that's why the current goes up like this, and it's just a straight vertical line here. So that is the simplest model of the diode, but it's not so accurate because a diode's behavior is obviously a lot more complex than that. A slightly more accurate, less simple model, but still pretty simple, is where you have the ideal diode here, which only conducts current in one direction, and it's perfect when it conducts current in the forward direction. And you also have this voltage source next to it, the E sub 0. Okay. This is the model that we often use in our circuit analysis. That E0 is the built-in potential of the diode, right? So the V0 of the diode. For most diodes, it's somewhere between 0.6 and 0.8 volts, depending on doping. All right, so in this type of situation, if you apply a negative potential to it, you'll get no current. If you apply anything below E0, you'll get no current. But once you apply anything above E0, you'll get a rapid increase in current. All right. So when you deal, I don't know if you ever you've done like LED type experiments or like other diode circuits in lab. You always put you can connect a voltage source to the diode, but if you do that, you have to be very careful that you don't go above 0.6 or 0.7 volts, because if you do, you'll just get like tons of current through the diode and you'll blow up the diode, right? So that's when you're thinking about it that way, like, hey, I can't put more than 0.6 or 0.7 volts across the diode, or else it'll just conduct current infinitely. Then you're thinking about this in terms of the ideal diode with an offset voltage. If you apply 0.2 volts to the diode, no problem. You'll get very little current. But once you get above like 0.6 or 0.7, then the current just shoots up. And then unless you have a resistor to control that current, the diode will just blow up. All right, then an even more accurate model, but still not the actual diode. A little bit more accurate is the ideal diode with offset voltage and resistance element to it. So the diode, I should have mentioned before that this built-in potential, you already know this, but the built-in potential is coming from the depletion region. The depletion region is where most of that potential drop occurs, right? So this element here is coming from the depletion region. The diode-like behavior, meaning like the ability to only conduct in one direction, that's also coming from the fact that you have a depletion region. This resistance here, the resistance is being used to model the fact that once you go above E0, once you apply a voltage larger than E0, the current will increase, but it won't increase like a vertical line like this. It'll increase as a non-vertical line with a large slope. Okay. Does anyone know where this series resistance comes from? Why does the diode have a series resistance? What part of the diode has that series resistance?
Neutral sides.
The neutral regions. That's right. So if we were to draw, we draw the diode, the P and the N material like this. Right, we're putting a voltage across it like this. All right, the depletion region forms, and that depletion region has this voltage drop across there. But then, the current is flowing through the entire device like this. So this N region is going to have some kind of resistance associated with it. This will also have a resistance associated with it. And this will be that voltage drop. So I'm just going to redraw the equivalent circuit here. Is you're going to have a resistance. This is due to the neutral region in the P-type material. Then you'll have the depletion region, which can be modeled as a voltage source and an ideal diode. And then you'll have another resistor here. So this is the resistance of the P region, and this is the resistance of the N region. And you can combine both of them. If you remember from circuits, you can actually combine those two resistances into a single resistor, and that's what you're getting down here. So this R is actually equal to the resistance of the P region and the resistance of the N region. So it's the sum of the two. Now you all already know how to calculate RP and RN, right? Because we did that in chapter 3. If you know the doping of the diode and you know the cross-sectional area and length of the diode, you can calculate its resistance. All right, so these are three models of the diode that can be used for approximations in circuits. We talked about this the first day of class, but I thought I'd touch on it again. We're talking about applications of the diode. Where are diodes actually used in circuits? And this, the very common application is a half-wave or full-wave rectifier. In the interest of time, we're not going to go over the full-wave rectifier. I'm just going to go over the half-wave rectifier because it illustrates the ability of a diode to rectify a voltage. Rectifying a voltage means that you are converting an oscillatory voltage, an AC voltage, and you're converting that into a DC or and only a positive voltage. So the oscillating voltage can go from positive to negative, but after going through the diode, it will only be positive. All right. The way a half-wave rectifier looks is like this. Let's say you have your sinusoidal input source, and this is I have a diagram of that here, but this sinusoidal voltage source is like, think about your power outlet. It goes from positive to negative. All right, and then you have the diode here. The diode only allows current to flow in one direction, and then you have a resistor here. So, the way you can think about the diode is that you have this ideal diode symbol and then like a voltage, this voltage across it. So it will only conduct current if Vs is greater than the built-in potential. So if the built-in potential of the diode you've calculated to be like around like 0.7 volts, then the diode will only conduct if more than 0.7 volts is, if this Vs is greater than 0.7 volts. You also have to include some voltage drop across the resistor too, but roughly like 0.7 volts of Vs is what you need in order to flow current in this direction. When Vs is 0 or negative, there's no current that flows through the diode. There's no current that flows through the resistor. So this output voltage basically goes to 0. All right, this is what it shows schematically. So this is the input voltage. Suppose you have, suppose you have a voltage that goes positive and then negative and then positive and negative. The diode is only a diode only conducts current when this voltage is above 0.7 volts. So you can see here when it's Vs minus 0.07, that's the output voltage here, because the voltage drop across. So imagine that this is Vs. So your input voltage is Vs. So imagine that you're right here on the map. There's a 0.7 volt drop across the diode, so your VO is Vs minus 0.7, so it's a little bit less than that. Okay, so it tracks when the voltage input voltage is above 0.7 volts, it tracks it. It's just a little bit smaller than it. But once that the Vs is less than 0.7 volts, at that point, the diode stops conducting current. And when it stops conducting current, that means there's no current going through this resistor. If there's no current going through this resistor, what happens to the voltage? So let's say the diode is off. If the diode is off, there's no current going through this resistor. If there's no current going through the resistor, then the voltage drop across the resistor is also 0. So the output voltage drops to 0. Right? So this is rectifying a positive and negative wave into something that's just positive. Now, if you want to build a DC source out of that, one thing you could do here is put a capacitor in series with this. And so what the capacitor does is that on the input cycle, meaning like when Vs is positive, you're getting current flow this way. And the current is going through the resistor, and it's also charging up the capacitor. Okay? And then when, here, I'll write this in blue now. When Vs is negative, then there's no current. So there's no current going through the resistor. And the capacitor actually supplies some of its charge to the resistor like this. And you end up getting a signal that looks... So what will end up happening is that the voltage will... The voltage will just decrease like this. And then it'll charge up again here, and then it'll decrease. It'll charge up, and it'll decrease like this. So when the voltage is positive, you have current going through the resistor, and you're charging the capacitor. So the capacitor is building up charge and storing energy. And when Vs is negative, there's no current going through the diode. So essentially, you just have this charged capacitor, and you have a resistor here. The capacitor discharges its charge through the resistor, and that's why you see the voltage decreasing here like this. And if it's a small capacitor, it would actually decrease all the way to 0. But if you choose a large capacitor, then it starts looking like this. And if you choose a really large capacitor, then it starts looking like this. And almost starts looking like a horizontal line.
Or more capacitor in parallel also?
You could add a large capacitor, or you could add more capacitors in parallel. Yeah, because parallel capacitors add. So this is how you convert, your wall outlet signal into a DC signal that can be used to charge your iPhone. There's obviously more components to it than this, but yeah, this gives you a general idea. One of the important applications of diodes. Application of Zener diodes. We talked about Zener breakdown in class last time. So the thing about Zener breakdown is it occurs at just a few volts of reverse bias. And you can design the diode to have a certain Zener breakdown voltage. All right. So let's look at, if we look at the diode characteristic here, let's say, for example, that we designed a Zener diode to have a breakdown voltage of negative 15 volts. So on the positive side, it works just like a diode would. All right, in this portion here, there's a small negative current here. But we designed the doping and other properties of the diode so that we can so our Zener breakdown starts to occur at negative 15 volts. So this is really interesting because we've designed it to have a breakdown exactly at a certain voltage. And so that acts as a voltage reference. When people are designing circuits, they're often very interested in having references, like reference voltages. If you want to get a voltage of 5 volts, what do? How do you actually generate 5 volts exactly? Yeah, that's a good reference. Yeah, batteries are good references, sure. But what if the battery starts to die out? So let's say, okay, let me give you a concrete example here. I work in some wearable devices, okay? Wearable electronics. A lot of the wearable electronics are powered by a lithium-ion battery. One of those like rechargeable lithium-ion batteries. The same stuff that's in your cell phone, okay? The lithium-ion battery gives 3.6 volts of output when it's fully charged. Okay, some of them give even more. They go up to like 4 volts of output when they're fully charged. But when they're but the problem is that when they start to discharge, after they're at when they're getting at like 10% capacity or 5% capacity, then their voltage actually starts to drop a little bit. When it gets to quite low, then the voltage drops like precipitously, and it'll go to like 1 volt or something like that. At which point your circuit is not going to work anymore, right? So the question is that like I want my circuit. You guys have designed circuits before in class, right? What's the first thing you put on your circuit is like VDD, right? You assume that you have a supply voltage, right? But what if your supply voltage is a battery where the voltage is changing over time? That's not good, right? Well, one way to deal with variable supply voltages is a Zener regulator, a voltage regulator. So the general concept of a voltage regulator is that whatever voltage you have coming in, it doesn't matter. You will have a fixed voltage coming out. So what's typically done in iPhones and wearable electronics, all these devices, they use something called a linear dropout regulator or low dropout regulator. So it'll take as an input any voltage between 3.3 volts and 10 volts, anything between there, or actually most of them are between like 3.3 and like say 4.3 volts. Any input from there, but the output will always be fixed at 3.3 volts, right? So this is why it's important to have a reference voltage. You want to have something in there that regardless of what's coming in will give you a fixed voltage that's coming out so that you can design your circuit around that fixed reference voltage.
How do you make something like that?
We're going to talk about one way of doing it here with the Zener regulator. But the low dropout regulators, they also have a different type of reference built into it, a reference voltage. The basic concept is this, okay? For the LDOs, the low dropout regulators, they measure the voltage that's coming out of the system. Let's say you want your LDO to work at 3.3 volts.
Competitor.
So you measure what's coming out at the output. You compare it to a reference. If they're not the same, then you bring in more power from your power supply, or you cut it off. That's the general concept. If this was a circuit design class, I would actually go into a lot more detail of that with you, but that's the basic idea. With something like a Zener regulator, this is a pretty easy way of doing it because the Zener diode acts as a voltage clamp. All right. I don't know how much you've talked about this in your previous circuits classes. I think what many of you know is that if you have an IV characteristic that looks like this, if you have an IV characteristic that's linear like that, where this is voltage and this is current, what kind of component is that? Resistor. What if the line is vertical? What does that mean? So here, notice that we have a vertical line. So the vertical, if you have a vertical element like that, that can act as a voltage reference, or what's called a voltage clamp. And I think the best thing to do is just look at an example here. If you have a circuit like this, let me zoom out here so you can see the IV characteristic also. The Zener diode, basically any voltage below negative 15 volts is going to turn into a short circuit. So when you have a vertical line like this, that means a short circuit. So let's look at what's going on here. So let's say we are applying a signal of 17 volts into the system. So this is our power supply. Our power supply is coming in at 17 volts, but it's a crappy power supply. So it's 17 volts plus or minus, so it's wiggling around 17 volts. Okay, we're trying to design some sensitive circuits, and we can't tolerate that wiggle in the 17 volts. We want to have a flat 15 volt output. So we go and we find a Zener diode that has a breakdown voltage of negative 15 volts, and this is what happens. So you have your signal coming in here, your power supply, then you have a resistor here, and then you have your Zener diode. Notice that this is the symbol for a Zener diode. When the signal, when the voltage is more than 15 volts, notice that the Zener diode is reverse biased here. Okay, so whenever there's more than 15 volts across here, this thing is going to act as a short circuit. So I'll just write that down. When Vs is greater than 15 volts, then all the current is going to go through here. And this thing acts as a short circuit, so your output voltage will start to drop. It won't be able to go beyond 15 volts. Okay, let me say that again. So when the voltage is greater than 15 volts, the diode is short-circuited. And when Vs is less than 15 volts, the diode is open-circuited. All right, so when it's greater than 15 volts, the current just goes through the diode like this, and when it's less than 15 volts, then the diode is open-circuited and there's no current going through here. So if there's infinite current going through the diode, what is your output voltage going to be? Well, actually, I don't know if that's a good way of looking at this. Let's look at it the other way. If the voltage is less than 15 volts and the diode is open-circuited, there's no current through here, right? So then you're able to have a current going into your whatever your load happens to be. All right. So, but the voltage at the output here, the output voltage here is equal to whatever you put into it. If the voltage is greater than 15 volts, so right now you can see here it's at 17 volts. Whatever excess voltage is going to cause this thing to turn on. Okay, and this is the key part. It's going to be short-circuited until it hits a 15 volt difference from the bottom to the top. So imagine the Zener diode like it's just turning off and on, off and on, off and on. Whenever it goes, whenever the voltage here is greater than 15 volts, the Zener diode turns on and all the current shorts through there. It shunts all the current. And when it's less than 15 volts, it's open-circuited. So the net effect of that is that it ends up clamping the voltage at 15 volts, right at 15 volts, the reference voltage of the Zener diode. All right, so just with two components, a resistor and a Zener diode, you created a linear regulator. You know, this may not be the best regulator out there, but it's pretty dirt simple to do. All right, so I hope that's clear. I mean, what you have to do is to think about this Zener diode as being short-circuited if you're greater than 15 volts. It's open-circuited if you're less than 15 volts, and the happy place where it likes to be is right at 15 volts. It's one way of thinking about it. Okay, so that's one of the two big applications of diodes. Zener diodes are voltage regulators, and then the standard diode is used in half-wave rectifiers or full-wave rectifiers for converting AC signals into DC signals. All right, now we're going to switch gears and talk about the transient behavior of the diode. So I've shown you this graph a few times now. We talked about the equilibrium behavior of the diode. This is where we didn't apply any voltage to it at all. Then we talked about the steady state situation where we applied a constant voltage to it. We talked about forward bias and reverse bias. And then we did the, now we're going to talk about the transient case where we're applying time varying stimuli to the diode. All right. So in the transient case, the carrier concentrations can change with time and the currents can be non-zero. All right, the difference between transient and steady state is that at steady state, the carrier concentrations don't change with time.
But when we say we inject the current, we inject the current internally, so it's already exists, but we just, when we have the energy band diagram, when we make the barrier lower, we let more carriers to cross. So we said that we inject the carriers. But here, like, it's like we inject this internally, so it already exists. We just like enhance the diffusion.
Are you talking about the transient situation?
No, the steady state.
Yeah, the steady state situation, you are, in forward bias, what you're doing is you're injecting carriers.
It's internal. It's already exists. We did not get any external carriers.
No, you actually are injecting carriers from the external circuit. Let's talk about that.
So you say concentration did not change.
I'll have a bigger whiteboard here. All right, so let's say you have a diode in, there we go. Yeah. So here's your diode. Here's your P material and the N side and the interface here. This is being connected to a voltage source like this. This is the depletion region in the middle here. So there is current going through here, right? Current means that holes are going this way and then electrons are going the other way, right? So those holes and electrons have to come from somewhere. So the voltage source is providing those electrons and holes.
And the concentration did not change?
The carrier concentrations don't change with time. That's the key part. They don't change with time. The carrier concentrations do vary as a function of x. They vary as a function of position. Remember we drew those out, like the carrier concentration profile. So yes, they definitely change as a function of position, but they do not change with respect to time. In the transient situation, they can change with time, and that's the difference. So the reason we care about this is is because there are many situations where the diode is actually being used in a non-steady state case where the voltages are changing rapidly. Remember, transient means we're applying a transient stimuli to it. So imagine that we're applying a time-varying voltage to the diode. Okay? What are examples? Can anyone think of examples where time-varying stimulus to a diode is important? I mean, I can think of a couple in my mind, which have to do more with optoelectronics, but I want to see if anything comes to mind for you.
LED televisions?
Yeah, LED TVs, right? So if you have LED TVs, those are LEDs are diodes, right? The LEDs have to change. You know, there's red, green, and blue LEDs, and those things have to generate images. And so these things are changing intensity at rates of 60 hertz, 100 hertz, like sometimes up to 240 hertz. Right? Those pixels are changing rapidly so that we interpret the changing brightnesses as a moving image. That's one example. So that's an example of something working in the 200 hertz range. What else?
So when you said transient, that means it's a pulse or like is sinusoidal wave like that?
It could be anything time varying. It could be sinusoidal, where you're just going from high to low.
Like
But it could also be like a pulse.
Yeah.
a single pulse.
So like the half wave rectifier also, you apply like this sinusoidal wave?
Yeah, sure. That's an example of a transient type behavior. We're applying a time varying stimulus. So that's the example of what this a half wave rectifier. Where if we plug it into the wall, our wall is 60 hertz, right? Mm-hmm. So that's an example where you're applying 60 hertz stimulus to it. The TVs you mentioned worked at a few hundred hertz. There's another example I'm thinking of where it's like much faster. It's very important to communication. So,
electrostatic discharge, they applied a very transient high voltage.
That's also an example of a transient stimuli, yeah. But I'm thinking about communication.
Fiber optics?
Huh?
Fiber optics?
Fiber optics, that's right. Fiber optics, we use light, and we transmit light over these fiber optic cables. And we have, I think I told you the first day of class, right? We have undersea cables that go between like the US and Europe and US and the rest of the world. They're literally at the bottom of the ocean. And there were some news reports recently because the US was worried about foreign nations like that were like, patrolling near the undersea cables. Can you imagine that? Like if like they decide, I think we'll just saw through there. That would be a disaster. But then that's one of the reasons why have you guys heard recently about Elon Musk's SpaceX, how they recently launched like 60 satellites into orbit? They launched 60 satellites several months ago too. So now they have a total of 120 satellites in orbit. They're basically going to use satellites for internet communications. So your satellites. So instead of going through these undersea cables, they're going to go up to the satellites and then bounce back down to other parts of the world. He's planning on having 60,000 satellites. They launched 60, but he's planning on launching like 30 to 60,000 more, and they're just going to be all over the globe. So like anywhere in the world, you're going to get internet access, satellite internet. It's like crazy. It's really, really cool though. Really cool. Where was I going with that? Oh, so that works on a different principle, but like the fiber optic communications, the way fiber optic communications work at a very, very basic level is that you have a fiber optic cable. On one end, you have a transmitter. So you'll have like a laser, a blinking laser or blinking LED, light emitting diode. And that's blinking. Blinking means you're sending ones and zeros across the line. That's how you send information. And on the other end, you have a receiver. The receiver is usually a photodiode. Okay? We'll talk a little bit about photodiodes, I think maybe in next class. A photodiode is a reverse bias diode that responds to light. Okay, so that's an example of a situation where you have a diode that's acting as the transmitter, and then you have a diode that's acting as the receiver. Okay, now does anyone know how fast fiber optic works?
Speed of light.
How fast do these LEDs have to blink? Typical fiber optics is working at gigabits per second. So that means this light is blinking at 10 to the 9th hertz. And the receiver has to be working that fast too. Okay, so when we're talking about transient behavior of diodes, this is what we're talking about. We're talking about the ability of an LED to blink very quickly, to turn light on and off, and we're talking about the ability of a photodiode to receive those signals and to convert that light into an electrical current very, very rapidly. Okay, so that gives you a framework for why we actually care about transient behavior. So 60 hertz is really easy to do. But like working at like 10 to the 9th hertz, gigahertz, is non-trivial. So one of the things we have to do, like the speed of a system can be limited by the circuits, by the electronics, but it can also, it's fundamentally limited by the components themselves, by the solid state devices themselves. Your LED and your photodetector has to be able to handle rapid changes in voltage signals. All right, So there's two ways of thinking about what limits the speed of a diode. The first one is a depletion capacitance, and the second one is what's called a charge storage transient. We'll start with the depletion capacitance first. Now, some of the transient behavior can be understood by looking at the diode light as a capacitor. This is good for those of you who've taken a lot of like circuits classes in the background and you've dealt with RC circuits. RC circuits, resistive capacitive circuits, have a low pass property, meaning they can't the voltage across the capacitors can't change very rapidly. Okay, so there's a whole like framework for that. If it helps you to think about that, then you can think about the depletion capacitance. But then the charge storage transient is a second effect that happens, which has more to do with the physics of the diode. So we'll go over both. So let's start with this. For those of you the few of you, the material science guys, if one of the important rules in circuit design, there's two rules, right? One about a capacitor and one about an inductor. The rule is this: is that for a capacitor, I is equal to C dV dt. All right. The dV dt is the rate of change of voltage across the capacitor. So imagine that there's a voltage across this capacitor. The rate of change of voltage with respect to time is dV dt. Multiply that by the capacitance, and then you get the current. So the current going through the capacitor is equal to C times dV dt. Now, what this equation implies, you cannot have infinite current. Okay, it's impossible to have infinite current. Because you can't have infinite current, you can't have an infinite change in voltage. The voltage can't change instantaneously. All right, because if it did, then dV dt would be infinite, and then you'd have an infinite current going across there, neither of which is possible. All right, so it takes time to change the voltage across a capacitor, and that's a central element of circuit theory. So a capacitor slows down a circuit because the voltage across it can't change instantaneously. The more capacitance it has, the slower the circuit is. All right. Similarly, the current in an inductor can't change instantaneously. We're not going to spend time on this in this class because we're not talking about inductors, but there's a similar rule that I just want everyone to be aware of. V is equal to L di dt. So the voltage across the capacitor can't change instantaneously. The current in an inductor can't change instantaneously. All right, so this is what a capacitor is. You imagine that we have like, it stores, imagine if we put a voltage across there, across a capacitor, we put a voltage source across there, then what will happen is you'll end up building positive charge on one side of the capacitor and negative charge on the other side of the capacitor. And we refer to that charge as Q. All right, so on the top plate of the capacitor, reminder to everyone, a capacitor is just like two metal plates near each other with a specific gap, small gap between them, a dielectric layer in between them. So Q plus appears on the top plate and Q negative appears on the bottom plate. Just like a PN junction where we said that the positive and negative charges have to be equal to each other, that's where this theory comes from. The basic capacitor, that the positive number of positive charges has to equal the net number of negative charges. So these are some of the fundamental relationships of a capacitor. The Q, the charge here, is equal to C times V. So it's proportional to the voltage that you put across the capacitor. If you double the voltage across the capacitor, you will double the amount of charge that's built up on the capacitor. So the Q equals CV. The units for Q is given in coulombs. So let's see, Q is charge, and that's in coulombs. The capacitance, that's in farads. So the capacitance C is given in farads. The dielectric constant epsilon, that's given in farads per centimeter. And then, the rest, voltage and current, the units for those already. So the definition of C is equal to dq dV, and you can do some electrostatics and figure out that it's equal to epsilon A over D. Epsilon is the dielectric constant of whatever's in between the two plates. So if it's air, then this is just equal to E0, which is 8.85 times 10 to the negative 14. Other materials multiply that by a certain factor, like anywhere between like 3 to 100 or so, if you have a really high dielectric material. And then D is the distance between the two plates. And then this relationship, which you saw on the previous slide, I is equal to C dV dt. Those are the important relationships for a capacitor. Now this second one, epsilon A over D, that one's important because that is what actually allows us to calculate the capacitance of a diode. So I already mentioned to you that the fact that you have positive charge here on one side and negative charge here on the other side, this looks a lot like the depletion region, right? That's the basic idea of the capacitance in the p-n junction. All right. So you have a buildup of positive charge on one side of the depletion region and a negative charge on the other side of the depletion region. This is a capacitor. All right. And so the simple way to think about this is that the capacitance is, I'll do the difficult way first and then we'll do the easy way next. The first definition of capacitance that we looked at here was C is equal to dq dV. All right, so you started off with Q equals CV, and so the capacitance is equal to dq dV. Change in current with respect to voltage. All right, so we've looked at this stuff already. We have equations for the amount of charge on each side of the depletion region. We know that they're equal to each other. We also have formulas for those. All right, these were the formulas if you don't remember from before. Q is equal to QAX XP0 times NA. So this is the charge on this side of the junction, or on the P side of the junction, and then this is equal to the amount of charge on the N side of the junction, ND. All right, so C is equal to dq dV. These are the formulas for the width of the junction. The reason why we're looking at that, okay, so we are putting Q in terms of XP0 and XN0. All right, and then these XP0 and XN0 is related to the width, and then the width is related to the voltage, because we derived these equations earlier. Okay, so we have equations, we have these different sets of equations. Okay, so what we know is that if you increase V, what's going to happen to the width? Think about this for a second. So V0 minus V over Q times 2 epsilon, the square root of that. If you apply voltage to the diode, what's going to happen to the width of the depletion region? It's going to decrease, right? Because you have this minus V here. Okay, so if you apply a voltage, then the width is going to decrease. Because the width changes, this amount of charge starts to change as well. All right, so if we want to calculate the capacitance in the p-n junction, the first thing we do is we put the total charge as a function of the width, and then we turn that into a function of the voltage. So you have this relationship. Again, basic equation is C is equal to Q equals CV. So C is equal to dq dV. So if you want to solve for the capacitance, the first thing you have to do is find an equation of Q as a function of V, and that's what you have here. This is your charge Q, and notice that this is now a function of V. All the rest of these things in the equation are just constants. All right? So this is our Q of V here. Now what we have to do is take the derivative with respect to V. And that's what we do here. So the capacitance is equal to dq dV. And if you take the derivative of this equation, which we're not going to do here in the interest of time, but if you were to take the derivative of that, you would get this equation here. All right, you know that like if you take the derivative of a square root term, so this is your variable v, you know, that's to the power of 1/2. If you take the derivative of something to the power of 1/2, you get something to the power of -1/2. So that's why you see the v up here in the denominator here. So it's to the power of -1/2. So this is just straightforward differentiation. Okay, so this thing in the box is the junction capacitance, or the depletion capacitance, as a function of V. So notice that as you increase V, this is the denominator is going to get less, so the capacitance is actually going to increase. Another thing to note about this equation is if you have a situation where NA is greater than ND, or ND is greater than NA, you know, this the denominator will simplify. So just keep that in mind. So a lot of the properties, it turns out, is determined by the doping on the lighter dope side. All right. Now, an easier way to derive the diode equation, you'll get the same result, but in my opinion, it's a little bit more intuitive, is you use this definition of the diode. The definition of capacitance, I'm sorry. Capacitance is equal to epsilon A over D. That's a very basic rule for parallel plate type capacitors. If we look at the depletion region as a parallel plate capacitor, so you have a certain amount of charge on this side, certain amount of charge on this side, you have a width of the depletion region. So what we do then is, if it's epsilon A over D, the epsilon, we take the epsilon of silicon, we take the area of this region, and then the D, the distance between the two plates, is just the width here, right? That's the key point here. The width of the depletion region is equivalent to D. So that's what we're doing here. Capacitance is equal to epsilon A over D, and we just replace the D with the W here. All right, so it's epsilon A over this whole square root thing, because this is the formula for the width.
What's epsilon again? Epsilon,
good question, is the dielectric constant. Okay, so you can look up the dielectric constant for silicon. I forget what it is off the top of my head. Maybe something like 3 times. I don't remember off the top of my head right now, but 3 or 11, I think it was. In any case, I mean, that will be given to you as a constant. Yeah, and so you'll be doing some calculations of this. So what is the typical capacitance of the depletion region? Now, notice that capacitance is equal to epsilon A over width. You know, these depletion widths are very small. They're in the micron range. So what's going to happen to the capacitance if you have a pretty small width?
So high.
It's going to have a relatively high capacitance. That's right. That's right. So that's one of the things that we have to be conscious of. All right. So at this point, you can think about that when you have a diode like this, if you have a diode like this as part of your circuit, whether that diode is forward bias or reverse bias, it doesn't matter. I've drawn this in the reverse bias state, is that when we draw the equivalent circuit for it, we have to consider that it has a capacitance associated with it. And even if we start incorporating, if we start talking about like the models that we did earlier, we say that, before we said here that the diode, these are the models, the circuit models for a diode. And so the appropriate thing to do in transient type cases is that you may also want to include this capacitance there as well. Because the capacitance will impact the transient behavior of the diode. So what we did right now is we basically just calculated the capacitance of the junction. All right, and this is the formula for the capacitance. And notice that this capacitance is actually a function of the voltage. So for those of you, again, who are, who've taken circuits classes, is that this is a typical capacitor element, and that has a fixed capacitance C. When we think about capacitors, we think that the capacitance is fixed. It's always going to give you that capacitance C. In the case of a diode, the capacitance of the diode actually depends on the voltage that we apply to it. So remember this just as a rule of thumb, is that, we talked about this in the equations also, but just remember it as a rule of thumb, is that when you increase the voltage, if you increase the voltage on a diode, if you increase the forward voltage, what happens to the width?
Decreases.
The width decreases. Depletion region actually gets smaller when you apply a forward voltage to it. Okay? With regards to capacitance, capacitance is equal to epsilon A over the width. So what's going to happen to the capacitance as you increase the voltage?
Capacitance is going to increase.
The capacitance will increase, exactly. And that's what we're seeing here. So when you apply a forward voltage, this depletion capacitance goes very high. And then when you apply a negative, when you apply a reverse voltage to it, then it starts going towards zero. Okay. So if we want our diode to work at high speed, would we want to forward or reverse bias it? Well, if we want it to work at high speed, do we want to have a large capacitance or small capacitance? Small capacitance, right? Large capacitance is bad for high-speed circuits. You want to minimize the capacitances everywhere. So if you want to minimize the capacitance of the diode, would you want to operate it in forward or reverse bias? Reverse. That's correct. Yeah, you can see it right here. This is the depletion capacitance on the y-axis. If you want to minimize the depletion capacitance, operate it in this region where it's lower. That's one of the reasons why photodiodes, if you want your photodiode to work at high speed, you have it at the end of your fiber optic communication line, right? You have these optical signals that are coming in at gigahertz speeds, and you want that photodiode to be able to convert those optical signals into electrical signals. So that, that's all the information so that you can browse Facebook. So you want, in those cases, you want, often those diodes are reverse biased so that you'll minimize the depletion capacitance and the diode will be able to work faster.
Sorry, but we want need larger W because C equals epsilon A per W.
Mm-hmm.
We need the larger W.
That's correct.
Because it's less than capacitor. And it is,
yeah, you're right. You want to increase W. If you want to minimize capacitance, then you want to have a large depletion width.
yeah.
So to get a large depletion width, you put it in reverse bias. Okay, good. So we covered this. So this is a little bit more detail on why the PN junction capacitance depends on voltage. So we know right now the width of the depletion region decreases as the square root of the applied voltage. So the more the more voltage, the forward voltage you apply to it, the depletion region gets smaller. So I guess one way to think about it is this is a diagram of the space charge region in the reverse bias. You can see here that you are in this example we're applying a reverse bias to it. Okay, so reverse bias means that the positive voltage is being applied to the N side and the negative potential is being applied to the P side. And this is an example of a P plus N diode. So you can see that most of the depletion region is on the N side of the junction. We haven't even bothered drawing the depletion region on the P side of the junction because it's so small compared to the depletion region on the N side of the junction. And what this diagram is showing is that as you increase the reverse bias, this width is going to increase. So it's going to the width is going to go from W to W plus some kind of delta. All right, and that's what this is showing here. If you increase the voltage, you'll increase the width. That's all this diagram is getting at. And if you increase the width, you end up reducing the capacitance. All right, but it's not a linear function. Just keep that in mind. It's a square root function. All right, that's why it's not a straight line. So it's sort of this tapering line. That's a square root function. All right, now we talked about the depletion capacitance. There's also something called a charge storage transient. This effect, it slows down the diode, all right? And I mentioned before that the depletion capacitance is really, it's intuitive for people who've done circuit design and they deal with capacitors, and we know capacitors slow down circuits. And so all we did is we derived a formula for the capacitance, the depletion capacitance. With this one, I want you to understand things a little bit more at the physical level. This is a charge storage transient. It's another effect which slows down the diode. And the way to think about it is that we drew these minority carrier distributions in this diagram before. Let me just remind everyone. This is the diagram that I'm talking about. We've gone over it many, many times. So you know how we drew these minority carrier distributions here in this diagram, right? So that's what we're going to go back to here. So what we're looking at here is, for example, we're looking at the minority, the whole distribution on the N side of the junction. Okay, so remember that if you have a diode in forward bias, I'm just going to draw this again to be clear. So you have a P and an N-type material like this. If it's in the forward bias, that means there's holes diffusing over this way and electrons diffusing over this way. As a result, on the N side, or this is on the N side of the junction, you have this distribution of carriers like this. So you have higher hole concentration at the edge of the depletion region. So this is X sub N. So this here is the edge of the depletion region. Okay, so the carrier concentration decreases exponentially with respect to X. That's what we looked at before, okay? So what I'm going to talk about now is the fact that, this is built up charge. Okay? So that charge exists when you forward bias the diode. So let's say we're applying a forward bias to the diode, and we've created this carrier distribution, and then suddenly we turn off the voltage. Okay? So it turns out that these charges that exist there, that concentration gradient of excess charges that are there, they don't disappear immediately. Why don't they disappear immediately? You guys actually know the answer to this question.
There's the lifetime.
Yes, exactly. Just like, we talked about an example where we applied a transient optical stimulus, right? In chapter 4, we said we're going to shine light on the diode. We're going to shine light on a semiconductor material. You generate these excess carriers, and then you turn the light off. What happens? Do the carriers go away instantaneously? They don't. They decay according to what kind of function?
Exponential function.
They decay as an exponential function with time, right? And the rate of decay is governed by the carrier lifetime, as Lama said. Okay? So similarly, the same thing happens with injection. We're not shining light on the material right now, but we forward biased the diode, and we created these excess carriers we created these excess carriers at the edge of the depletion region. When we shut off the forward bias, we shut off the voltage. Those excess carriers, they don't go away instantaneously. It takes some time for them to recombine and go away. All right, that recombination time, that carrier lifetime, it can be small. Like it can be on the order of, it could be nanoseconds or microseconds, but that seems like a really, really short amount of time. But when if we're trying to operate the system at gigahertz rates, then those things start to matter. Okay. So this is what the carrier distribution looks like at time equals 0. And then over time, it just gets less and less until at some point it just becomes a flat line like this. Those excess carriers disappear. And this time, the rate of decay is e to the negative t over tau, where tau is the carrier lifetime. All right, so the input here is we applied a voltage to it, and we got some kind of forward bias current. At t equals 0, we shut the voltage off, and so now we're not applying any voltage or current to the system, and so these excess carriers take some time to disappear. So as a result of that, there's some funky things that happen in the diode if we supply a square voltage wave to it. All right, so what we're doing here is, in this particular example, we have the diode connected. In the forward bias type configuration, well, not forward bias, we're going from forward to reverse bias, okay? We have a voltage source connected to it, and that voltage source is connected to a square wave generator. The square wave is going from positive voltage to negative voltage, right? So we have positive voltage here, negative voltage here. So this is the input voltage that we're applying to the diode. We're going from forward bias to reverse bias, back to forward bias, back to reverse bias, and we're doing that quickly. So the funny thing that happens here is that, let's say we applied the forward voltage, we get a forward bias current, nothing weird about that. Then we switch to, we switch from positive to negative voltage, so we switch to reverse bias, and the current goes to the current is supposed to be. Let me ask this: what is the current supposed to be at reverse bias? If you reverse bias a diode, what do you expect to happen to the current? Is it going to be high or low? It's going to be low. Right? Remember, a diode conducts current in one direction, right? So if you put a negative voltage across the diode, we expect the current to be 0. But watch what happens instead. This is interesting. What you would think is that the current should just go to 0 like this. You know, if you apply negative voltage to the diode, it should just have a small negative current. But instead what happens is that it actually goes negative like this. It goes to like a negative reverse current for some amount of time, and then it decays. To 0. This feature that you see here, this extra, where it switches over to the negative current, that is because of the charge storage transient. Once this charge gets drained, then only then does the current go to 0. Okay, so this is showing the voltage, the voltage across the depletion region as a function of time. It's actually decaying to the negative potential. Initially, that voltage is positive because of the charges, the excess charges that exist there. Right. So if you have all these, if you have some positive charges that remain there, that's going to create a potential, and that takes some time for that potential to die out. All right. So you get these interesting effects when you because of the charge storage transient, and those are things that people have to be careful about when they are operating the diode at high speeds. Okay. So it looks like we have about 5 minutes now. So this is what we've covered with the diodes. At this point, we're going to now go on to metal semiconductor junctions. So I want to ask everyone if there's any questions on diodes related stuff. Okay. We talked about the diode at equilibrium. We talked about the diode at forward bias. We talked about the diode, certain aspects of the diode at transient behavior. We also talked about some non-ideal behavior of the diode, not just these charge storage transients, but other things like avalanche breakdown, Zener breakdown, and so on. Okay, a lot of different aspects of diodes that we talked about. So to wrap up the diode portion of it, I would make sure that you go over the problems in the homework about the diodes. And as we go into the metal semiconductor junctions, know that there's actually going to be some similarities between metal semiconductor junctions and diodes. So that's why they're part of the same chapter. Since we only have a few minutes left, what I'm going to do is just give you a quick introduction to the metal semiconductor junction, how it works, and so that we can touch on it and then come back to it on Monday. So with metal semiconductor junctions, with diodes, what we did is we said, okay, we have a p-type material and n-type material together. We put them next to each other, and then we talked about the depletion region that forms and all the cool physics that happens because of it. Metal semiconductor junctions is when we say we're going to take a metal and we're going to put a semiconductor and we're going to put them on each other. What happens at the interface of the metal and the semiconductor? It turns out two things can happen. One is a Schottky barrier, and the other one is an ohmic contact. And it turns out the Schottky barrier actually has the properties very similar to a diode. In fact, very similar to a one-sided junction. And then another situation that can happen is an ohmic contact, and the equivalent symbol for this is just a resistor. Okay. The reason why metal semiconductor junctions are very important is because we have these semiconductor materials, but ultimately they need to be connected to a circuit, right? So at some point, you got to put metal on the semiconductor to make a contact. So if you just assume that your contact is going to have no effect on the circuit, that would be naive. It turns out that the interface of the metal and the semiconductor also have some interesting properties that we have to be concerned about. If you want to make a nice contact of the semiconductor, then this is what you want. You want an ohmic contact. But sometimes if you don't design it properly, you may end up getting a Schottky barrier, which will have diode-like properties instead of an ohmic contact. And in some cases, you actually intentionally design a Schottky barrier diode because you want diode-like properties. Actually, I don't think we're going to have time to get into this today. No. So we'll get into this next class. Yeah. So any questions on diodes? Any questions on the class project? That's going to be due Monday. Nadine, do you have a question?
Yeah. It's not about the project or this. I don't know if you said it last time, but is the final cumulative or is it just whatever we do after the first exam?
It's not going to be cumulative. It's going to be after the first, all the stuff that we covered after the first exam.
So do you know how many modules? Are we going all the way to 8? So is it, I know we have module 5.
We are probably going to end up covering, just gauging by the amount of time we have, we're probably going to end up covering diodes and we'll get through MOSFETs.
Okay.
We're going to touch maybe a little bit on photodiodes, but no, we're not going to get through all of chapter 8. It's not going to happen. I was wishful thinking. Other questions? Sadi?
Is it common that using some type of diode in integrated circuits, such as tunneling diode or Zener? Because I read in the tunneling diode, it is hard, and some of the articles about PVT use some ways such as calibration, not diode or other.
You said
PVT, parameter, voltage, and temperature change. They didn't use something such as they used some way such as calibration in integrated circuits.
You're saying they use components other than diodes?
No, they didn't use a diode. They used other way, and I think putting diode in integrated circuit may have some problem.
So your question is why aren't diodes put into integrated circuits?
Yeah, I think it's common that using diode in integrated circuit or.
Well, I mean, diodes are used in some types of circuits, but if you look at the majority of integrated circuits today, almost all of it is like digital microprocessors. So the digital microprocessors are all like MOSFETs, NMOS, PMOS devices. The diodes, I would say, they're used for, electrostatic discharge protection. And because a MOSFET has N and P regions, it's going to have some diode-like properties that you have to be careful about if you don't design it properly. In terms of integrated circuits, a lot of light sensors use diodes. Yeah.
For voltage generation, I think they didn't use diodes.
Oh, you're talking about voltage generation. Yeah. Good question.
Voltage.
Yes. Okay, that's a good point. Then with integrated circuits, they use other types of references.
Yeah, for example, calibration, they use some other type of circuit and use the feedback of the circuit to fix the voltage, and they didn't use the diode.
That's right.
Okay.
So
I
there's.
think it is hard to put the diode in integrated circuit. I'm not sure, but
Well, one of the issues, that's a good point. So your point is that diodes are often not used in integrated circuits as voltage references.
yes.
So the example that I gave you today with Zener diodes are often, you'll be able to buy a Zener diode at, off DigiKey or something. If you want to make a voltage reference as a discrete component on your breadboard, that's one of the uses of Zener diodes. For integrated circuits, I've seen there's so many different types of circuits that are used as voltage references. Some of them very, very complex and very interesting. Other ones are less so, but there's a whole bunch of different things that can be used as references. It doesn't have to be a diode per se. There's a lot of different effects in semiconductor devices that can be used. I'm trying to think of one off the top of my head. I can't remember the name of it, so I can't share that with you, unfortunately. But one of the things they do, like they try to make the reference a fixed voltage, and they try to make it as independent of temperature as possible.
Yeah.
That's what you want. Yep.
And usually use the Zener to protect the gate of the MOSFETs, like if any transient voltage or.
Well, the diodes that are used to, yeah, sometimes they can be
So you can like
right.
protect the gate.
Yeah, you can use clamping diodes to protect the gates of MOSFET devices. Yep.
Thank you.
All right. Yep. Good questions. Thank you.